Welcome back everybody. In this chapter, we're diving into one of the most important topics in switch and spanning tree protocol. Redundancy is essential in any network. It keeps us online when links fail and protects us from downtime. But if redundancy isn't controlled properly, it can completely take down a layer 2 network through broadcast storms and switching loops. That's where spanning tree comes in. In this chapter, you'll learn how STP prevents loops, how the root bridge is elected, how port roles are determined, and how to configure features like PortFast and BPDU guard in a Cisco environment. Let's get started. When expanding a layer 2 network, physical redundancy is essential to maintain connectivity if a switch or link fails. However, redundant paths can introduce layer 2 loops, leading to broadcast storms and network instability. In this chapter, you'll learn how spanning tree protocol prevents these issues by detecting and blocking loops. The topics covered in this chapter: what spanning tree protocol is and why it's needed, spanning tree standards, STP port roles and states, root bridge election and path selection, and configuring and troubleshooting STP. So what is spanning tree protocol? STP is a core CCNA topic that focuses on preventing layer 2 loops in switched networks. In real-world networks ranging from small businesses to large enterprises, multiple switches are interconnected to provide redundancy and high availability. These designs commonly follow Cisco's 3-tier hierarchical model, which consists of the core, distribution, and access layers. This model is recommended because it supports scalability, redundancy, and the use of Ether channels to increase bandwidth between switches. However, while redundancy is essential for fault tolerance, it can also introduce serious problems if not properly managed. At layer 2, redundant paths can create loops. When a broadcast frame is sent, such as one with the destination MAC address of this, switches will flood it out of all ports except the one it was received on. In a loop topology, this broadcast frame is continuously forwarded between switches, creating a never-ending cycle known as a broadcast storm. Over time, this consumes bandwidth and CPU resources, eventually crippling the network. Spanning tree protocol solves this problem by acting as a layer 2 loop prevention mechanism defined by IEEE 802.1d. STP logically builds a loop-free topology by allowing only one active path between switches, while placing redundant links into a blocking state. Switches exchange bridge protocol data units every 2 seconds to identify redundant paths and determine which links should be blocked. If an active link fails, STP automatically reconverges by moving a previously blocked path into a forwarding state. This ensures continued connectivity without introducing loops, providing both redundancy and stability in the network. Spanning tree protocol uses bridge protocol data units to monitor the network and detect topology changes. By default, STP is enabled on Cisco switches, and each switch sends BPDUs every 2 seconds to exchange spanning tree information with neighboring switches. Each BPDU contains key information that allows switches to elect a root bridge and identify redundant paths. We have the bridge ID. This identifies each switch in the spanning tree process. It consists of a priority value and a MAC address. Default priority on Cisco switches is 32,768. The priority values range from 0 to 61,440 in increments of 4,096, and lower priority values increase the likelihood of a switching becoming the root bridge. You have Extended System ID. This represents the VLAN ID for the spanning tree instance. Cisco switches run a separate STP instance per VLAN, meaning multiple spanning tree processes can operate simultaneously. And then MAC address, a unique identifier used to distinguish switches when priority values are equal. The switch MAC address can be viewed using the show version command. The information carried within BPDUs allows switches to elect a root bridge, determine the best paths through the network, and detect link failures. If a BPDU is no longer received on an active path, spanning tree automatically recalculates the topology and activates a previously blocked path to maintain connectivity without creating loops. In a switch network, one switch must act as a central reference point for all layer 2 paths. This switch is known as the root bridge. Its role is to ensure there is only one logical forwarding path between switches while redundant paths are placed into a blocking state to prevent layer 2 loops. the root bridge is elected based on the lowest bridge ID, which is made up of bridge priority, the extended system ID, and the MAC address. If all switches have the same priority, the switch with the lowest MAC address becomes the root bridge. Once selected, all other switches calculate their best path toward the root bridge and forward traffic accordingly. Using the show spanning tree command, a switch displays root bridge information and local switch bridge information. From this output, you can determine details such as the VLAN the spanning tree instant applies to, the spanning tree mode, the root bridge priority and MAC address, the root port cost, which indicates the interface speed, and default timers, such as the 2-second hello timer. Spanning tree also uses path cost to select the best route to the root bridge. Lower cost paths are preferred, with faster interfaces having lower costs. For example, Gigabit Ethernet is preferred over Fast Ethernet. By default, STP automatically elects the root bridge, but this is not best practice. If left unmanaged, a switch in the access layer often lacking redundancy could become the root bridge. For this reason, network professionals manually configure a core or distribution switch as the root bridge. To improve resilience, a secondary root bridge should also be configured. This is done by assigning a priority value slightly higher than the primary root bridge. If the primary root bridge fails, the secondary root bridge automatically takes over. In networks with multiple VLANs, each VLAN has its own root bridge. Rather than using a simple switch as the root for all VLANs, best practice is to load balance VLANs across multiple core switches. This distributes processing load and improves fault tolerance. If one core switch fails, the remaining switch temporarily becomes the root bridge for all VLANs, ensuring continued network operation. STP is a layer 2 loop prevention mechanism that is enabled by default on switches. It is defined by the IEEE 802.1d standard. While STP is an open standard, Cisco does not strictly implement the original IEEE 802.1d version. Instead, Cisco uses its own enhanced implementations such as PVST+, which runs a separate spanning tree instance per VLAN. Spanning tree assigns specific port roles and states to control how traffic flows through a switched network and prevent layer 2 loops. The STP port roles, root port, the port on a non-root switch with the lowest cost path to the root bridge. Each non-root switch has one root port, and root ports never exist on the root bridge itself. Then you have designated port, a forwarding port on a network segment that allows traffic to flow away from the root bridge. Designated ports are always in a forwarding state. And alternate backup port, a redundant port that is placed into a blocking state to prevent loops. These ports provide backup paths if the active path fails. To view port roles and states on a Cisco switch, use the show spanning tree command. When a switch boots, interfaces do not immediately forward traffic. Instead, they transition through the following states. Blocking, does not forward user data, receives BPDUs only. Listening, processes BPDUs but does not forward frames or learn MAC addresses. Learning, learns MAC addresses but still does not forward frames. Then forwarding, fully operational state, forwards user traffic and processes BPDUs. And disabled, administratively shut down by the network administrator. These transitional states ensure the network remains loop-free while spanning tree converges. Now that you understand spanning tree standards along with port roles and states, the next section focuses on systematically identifying the root bridge and port roles within a network topology. An essential skill for any network professional is the ability to analyze a spanning tree topology and correctly identify the root bridge and all port roles. By applying a simple rule, structured approach, this process becomes straightforward and repeatable. Rule of thumb for identifying STP roles: always work through spanning tree in the following order. 1. Identify the root bridge. 2. Identify the root ports. 3. Identify the designated ports. And 4. Identify the alternate blocked ports. So identifying the root bridge. The root bridge is the switch with the lowest bridge ID. So switch 2 as the lowest bridge ID and is therefore elected as the root bridge. Identify the root ports. Root ports are the ports closest to the root bridge on non-root switches. So switch 1, Fast Ethernet, connects directly to switch 2, the root port. Switch 4, Fast Ethernet, connects directly to switch 2, root port. On switch 3, there are two equal cost paths to the root bridge. Switch 3, switch 1, switch 2, and switch 3, switch 4, switch 2. Since the path costs are equal, the tie is broken by comparing the bridge IDs of switch 1 and switch 4. As these are also equal, the switch with the lowest MAC address is selected. This makes switch 3 fast Ethernet the root port. Identifying the designated ports. All ports on the root bridge are designated ports. Switch 1 is designated as it forwards traffic toward the root bridge for switch 3 and identify the alternate port. To prevent a layer 2 loop between switch 3 and 4, one port must be blocked. Comparing bridge IDs, switch 3 wins the election for the forwarding role. Switch 3 becomes the designated port, switch 4 becomes the alternate port. Even though switch 4 is blocked, connectivity is not lost. Spanning tree ensures traffic flows the active path, so switch 3 to 1, 2 to 4, and this returns traffic flow along the same logical path in reverse. Understanding how to systematically identify the root bridge and port roles is critical for real-world troubleshooting and for success in the CCNA exam. In the next section, you'll explore Cisco's proprietary spanning tree implementation, PVST+. Cisco enhanced the IEEE 802.1d spanning tree standard with its proprietary implementation called PVST+, which is enabled by default on Cisco iOS switches. Unlike traditional STP, PVST+ runs a separate spanning tree instance for each VLAN, allowing better control, redundancy, and load balancing across the network. PVST+ supports interoperability with devices running standard IEEE 802.1d STP, making it suitable for mixed vendor environments. PVST+ uses the same port states as traditional STP: blocking, listening, learning, forwarding, disabled. Networks running STP or PVST+ typically take 30 to 50 seconds to converge, which can be significant after power failures or topology changes. Multiple spanning tree protocol, defined by IEEE 802.1s, improves scalability by using a single spanning tree instance to manage multiple VLANs. Rapid spanning tree protocol is a faster version of traditional STP, defined by IEEE 802.1w. Unlike IEEE 802.1d, which can take 30 to 50 seconds to converge, RSTP can reconverge a network in approximately 2 seconds. Cisco implemented RSTP as a proprietary enhancement called Rapid-PVST+, which runs a separate rapid spanning tree instance per VLAN, similar to PVST+, but with much faster convergence. To enable Rapid-PVST+ on all Cisco iOS switches, use the following global configuration command: spanning tree mode Rapid-PVST. Rapid-PVST+ simplifies port states compared to traditional STP. Discarding. Similar to blocking, does not forward frames or learn MAC addresses, only sends and receives BPDUs. Learning. Learns MAC addresses and populates the CAM table but does not forward frames. And forwarding. Fully operational state, forwards frames, learns MAC addresses, and processes BPDUs. The key difference: Rapid-PVST+ removes the listening state. Ports no longer need to wait before learning MAC addresses, which significantly improves convergence speed. Rapid-PVST+ fully supports features such as PortFast, BPDU guard, BPDU filter, root guard, and loop guard. Here we have PortFast. This allows a port to transition immediately to the forwarding state. This feature must only be enabled on edge ports. We have edge ports. Ports connected to end devices, not switches. Edge ports can never receive BPDUs. To enforce this, BPDU guard should be enabled alongside PortFast. BPDU guard. If a BPDU is received on a PortFast enabled edge port, the interface is placed into a ERR disabled state, preventing potential layer 2 loops. The security benefit: BPDU guard also prevents rogue or unauthorized switches from being connected to the network, protecting the topology from accidental or malicious loops. Rapid-PVST+ provides fast convergence, improved scalability, and enhanced protection for modern enterprise networks. Summary: In this chapter, you explored how physical redundancy can both improve network resilience and introduce serious issues such as layer 2 loops. You learned how spanning tree protocol prevents these loops and protects enterprise networks from broadcast storms and instability. By completing this chapter, you gained the ability to identify the root bridge and port roles within a spanning tree topology, configure primary and secondary root bridges, and implement PortFast with BPDU guard to protect edge ports. These skills are essential for real-world Cisco networks and form a key part of the CCNA exam objectives. In the next chapter, you'll shift focus to layer 3 concepts and learn how routers determine the best path to destination networks. Keep building and keep practicing. I hope you enjoyed this video. I'm CyberEd, and I'll see you in the next one. Peace.